Another new amp for the workshop. I've not had this particular model in before. It is, as the badge explains, a Vox. Now this is one of the 50th anniversary models that they did. This is the 15H1 TV. TV meaning obviously it's the TV style cabinet. They did also do one in a hardwood cab. But yeah, I think there was they did an AC30 version as well. But this one is quite interesting because it's not PCB inside. Apparently it is hand wired on turret board, so it'll be interesting to get inside, have a look, see what's going on. It's come in for what we think might be quite a serious issue in that it keeps blowing its mains fuse. Now, there is a bit of confusion about which mains fuse it should have or what current rating that mains fuse should be. But the brief story is that it's blown fuses in the past. It often does it when you initially turn it on, although the owner is unsure whether it's actually blowing when you switch the amp off, and therefore the next time you go to play the amp, it's dead. But he says sometimes the dual light flashes and then the amp dies. Now, the panel next to the fuse holder in the IEC socket says it needs for UK mains voltage a 1 amp fuse. The owner's manual that I found online for this particular model also says, sorry, that's the AC. Here goes the AC15. Sorry, my mistake. 1 amp fuse as well. So, and it's the same if it was 240 volt Australia, a 1 amp fuse. Now, he has been running a 1.5 amp fuse. It kept blowing, and so he apparently there was some information he found online where most people actually run these with a 2 amp fuse. Now, that doesn't sound right to me. Does not sound right to me at all. I would be surprised if a 15 watt amp needs a 2 amp mains fuse at 240 volt, which would, implies it's pulling 480 watts out the wall. Right? Yeah, no, absolutely not. So there's clearly something weird going on. So we're going to have to investigate that. The amp is currently dead, so we do need to check what fuse is in the socket at the moment, what the value of it is. We're going to pull the chassis out, give it a visual inspection, and then we're going to soft start it on the bench through the light bulb limiter and see if we can work out exactly what is going on and where. But first, before we do anything like that, let's just have a quick look around the amplifier and go from there. I just zoomed you in a little bit. We're now on the Susan, so we can spin this thing around. It's a lovely, absolutely lovely blonde Tolex. I do love this particular Tolex pattern. It's quite a smart looking amp, I will admit. It's very smart looking. Lovely 12-inch blue in the back. AC15 H1 TV is the model number. And if we bring you up to look at the top panel, hopefully you can, maybe you can't. I don't have the reach on the, but yeah, you can see it's a lovely black control panel with gold logo lettering on with the cream chicken head knobs. I do like that. I think that looks really smart. So but there we go. Confirmation on the back. This is saying 220 or 230 volt mains, 50 or 60 hertz. We should be pulling around 100 watts out the wall, which would imply that it should be drawing around half an amp out the wall, and therefore 1 amp would be correct if it's its main fuse, 1 amp slow blow, but that's clearly not what's happening. As I said, it's got blue in the back, and the customer did bring the mains cable that he uses with the amp, so we can test this as well, just in case there's something going on with that. I highly doubt it, but it's nice to have it here, just so we can eliminate that as any issue. So I'm going to pull the chassis now. If it's built the same as a normal AC15, we should be able to take this back panel off first, and then it's going to be the 2 screws on either side should release the chassis from the cabinet, and we'll be able to pull it out. So let's get ourselves a little plastic pot to put our screws and bits in, and then we can have a look inside. So we've got some chewed up screws on the back here. They are Phillips. Phillips number 2. 2 screws on the vertical are actually screws. Because they are going into wood. But the ones along the top, at least the first one I've taken out, is a machine screw. Now a machine screw, for those that don't know, and I'm sorry if I'm teaching you to suck eggs here, but a machine screw looks like a screw from this end, but looks like a bolt from this end. All right, so it's a bolt with a screw head, whereas a screw itself has got the pointed end. You see? Oh, what's going on with my hands today? So machine screw, screw. And a machine screw with a hex head or an Allen head is called a bolt. Okay, rear panel off. Can you all see? You can. There we go. So it's interesting. I wasn't expecting that. It's zoom you in. We've got the valves on a separate board here. I like that. Got a nice yellow print mallard there. We've got, come on, behave. A white print mallard there. We've got a nice selection of valves in this. Very nice. That looks like another white print mallard. No, it's a yellow print. God, these fetch some big money now. And the EF86, I don't recognise that. I don't recognise the design, anyway, or the brand. But anyway, look at the board behind. You can see we've got turrets on like a pseudo PCB. So there is a printed circuit on the back side, but all the components are on the front side here on turrets. Okay, we've got some what look like quite cheap capacitors. So we'll check those, make sure they're not leaking, make sure there's no any issues with that. Let's undo these. So there you go, quite a long, it looks like a bolt, but it's got a screw head, so it's called a machine screw. Okay. Don't you lot dare complain that I never teach you anything. So being an AC15, we are expecting a pair of EL84s and an EZ81 rectifier valve, which is a 9-pin valve. It looks like a short EL84. Okay, so I'm just going to remove this. We'll stick it down on the bench and then we can have a look in more detail. Closer look then at that lovely screen print along the top. Very smart. So we've got 2 channels. Channel 1, volume and a brilliance control, which is a 3-position switch, off, 1 and 2. Got a bias shift slider switch here, along with a pentode triode switch for the EF86. EF86 is a pentode valve, a sharp cutoff pentode, if I remember correctly, but you can choose to run that in triode mode. It's a very similar operation I would expect to how a pentode triode switch works in the output stage. At channel 2, we've got 2 inputs, volume, treble and bass. We've got a top cut control, which will be post phase inverter as is standard on these. We've got a pentode triode switch for the output valves and our simple on-off switch at the back. Transformers, we've got the Sane Core Music Instrument Company, easy for me to say, dated December 2012 and appears to be the same on the output transformer. Okay, so that they've utilised the original AC15 design, chassis design, with this L-shaped chassis. So in order to access the components under this side, we are going to have to remove the chassis from this mounting board and have a look. But whilst we're here, we've got a HT fuse in here, so let's check that as well. It says 250 milliamp time delay fuse. Now with these type of fuse holders, again, apologies if I'm teaching you all really basic stuff here. It's not just an unscrew, it's a push down and unscrew. And that will get you released. The focusing on my camera today is absolutely rubbish. There we go. 250 milliamp, T for time delay, F would be fast blow, and it appears to be intact. We can just test across it with a multimeter, but I'm not going to do that for the time being. Not now that it's easily accessible whilst it's on the bench. So again, to reinstall that, push it down first, twist and up. Okay, so there's your EZ81 rectifier valve. So we've got a JJ, no signs of discoloration, so it hasn't been running too hot. Looks to be all right, doesn't it? This EL84 here has got signs of discoloration, which means this one has been running quite hot. Probably well over its rated dissipation, which is a shame. Its sister valve, again, some slight discoloration there. So we've got quite an abused set of output valves. Is that an indication as to why this amp is blowing fuses? Okay, let's remove. Actually, no, I'll tell you what we're going to do. We'll stand it up on its end. And I'm just going to pull. I need 3 hands for this, bear with me. There's the IEC socket. As you can see, it says on there 1 amp fuse. Let's pop that door open. Okay, so the one that will actually be in circuit is this one here. So it's got a spare holder as well. So it's got a 1 amp fuse in it. Okay. Not sure about that filament. That doesn't look right, does it? What about the spare one that he's got in here? Oh, that's a much thicker filament. That's it. Well, that's a 1 amp as well. I'm not happy with these fuses. Okay, while we're at it, we'll just inspect the socket itself, make sure there's no signs of arcing or scorching going on. Make sure there's no issues with that socket, and we can just spin it round. We can just check the other side as well. God, you can't see that. Just looking for signs of anything that's not quite right. I don't see anything. Okay. So questions about those mains fuses. Remove the chassis from this lower board. All right, big reveal time. Very interesting. So now I've got access to the 4 preamp valves, and for the sake of argument, I do include the phase inverter in the preamp section. Okay, Future Chris here. It's amazing what you spot when you are editing a video, putting things together. I've just spotted, and I've just run over and checked on the chassis itself, that quite a big issue that I didn't see when I was actually filming this, because obviously, you know, I'm looking at other things at the time, etc, etc. I know some of you like to shout at me for missing stuff, but you try filming stuff and concentrating. It's more difficult than it looks, so again, forgive me. Anyway, but I've just noticed that the speaker selector is set to 8 ohms. Yet the amp is loaded with a 16 ohm Celestian Blue. So how long has this amp been running with a mismatch? Now, in an amp that already runs its output valves and things really hard, that's not good, right? It's not good at all. Now, I also know that the owner has been using an attenuator with this amplifier, so even more stress on stuff, right? So perhaps that's going to offer us a big clue to why this amp is playing up. Anyway, back to the video. We'll talk about that another time as to why I personally do that. I understand it's not, but as far as I'm concerned, or as far as I prefer to work, it is, and we will get into that. Here's the output stage, the output board. Again, it's got some cheapy filter caps in, but for a 2007 amp, so we're talking, what, we're coming up on 18 years old now? Is that right? Oh dear. Maybe it's time to swap those out. Let's look at the output valve socket, see if there's anything obvious going on down here that might give us a clue. So we've got some signs of arcing on this socket. Screen stoppers, got 100 ohm screen stoppers up on the board here. They appear to be okay. 130 ohm cathode bias resistor. Sorry, I'm not showing you what I'm looking at. I do apologise. Here it is. Now, I would argue that it's probably a bit low at 130 ohms, and that's probably why our output valves are running too hot. But again, there's nothing immediately obvious or burnt. Oh, look, there's another fuse on the board here as well, which is 6.3 amp fuse. So that'll be for the heater circuit, this one here. Oh, both of those resistors there, these 100 ohms, both showing signs that they are quite hot. Can you see? Well, they've got hot in the past. So these will be the heater balancing resistors. So maybe we've had a heater short in the past. Or we've got one now. Okay. So I'm going to quickly test the fuse that was in the amp. Then I'm going to continuity check. It was the two fuses there. Is this one? But if the fuse is good, it should beep. Nope, that one's popped. What about the spare one? Okay, so the one that was in was popped, but the other one is good. So we'll reinstall that one. Excellent. Let's take this thing over to the bench and fire it up through the light bulb limiter. Right, amp is on the bench, all hooked up. So we've got the a known good mains fuse now installed in the amp, and we've got all the valves in place. I've got my 8 ohm dummy load connected, and we're going to fire it up in restriction mode, which means our 100 watt light bulb will be in circuit. Now, if that bulb glows really bright, full brightness, then we know there's a short inside the amplifier that's going to need fixing. So amp in the amp switch in the on position. All my other controls at 0, and then I'm going to control the power to the amplifier with this switch here. Got everything else ready to go, and we're watching this light bulb. Okay, so there was an inrush current there. You saw the bulb glow ever so slightly bright, and now it's warming up. So it's currently pulling 28 watts out of the wall. In fact, if I bring you around, you'll be able to see. There we go. So the amp's currently warming up. Now the valves are warming up. We're getting more current draw, which is being indicated by the light bulb, and I would expect to see the amp to settle down now at around where it is now, around 36, 37 watts. The bulb isn't glowing at full brightness, so we haven't got a fault current flowing inside the amplifier. We're just going to leave that to settle for 5 minutes or so, then we'll come back. Okay, a couple of minutes now. All seems to be nice and stable. So I'm going to remove the light bulb from circuit. So I'm going to give the amp full mains voltage. So this thing is rated, what was it, 100 watts maximum. So I'll probably expect this to go up to around 95 watts consumption out the wall, maybe. We'll see. Let's find out what happens. And she dead. And she dead. Okay, very interesting. Back on restriction mode. I did actually hear something arc then, which I think was the rectifier valve. But why didn't the HT fuse pop? Why did the mains fuse pop? So let's just zoom you out. You can get a nice view again. Mains fuse. Okay, here's the fuse. Oh yeah, she went bang. Right, let's get another one. 1 amp. Another 1 amp going in. Hook the mains supply back up again. Restriction mode. And we're on. This time, let's watch that rectifier valve. Oh, we're in restriction mode. Did you see it then? I think we've got a shorted rectifier valve. Okay, so I'm not going to give it full power because we know how that one's going to end up. So let's get another EZ81. Okay, another JJ. This one is brand new out the box. Let that warm up. Okay, let's give this thing full power. See what the rectifier valve does. So you can see the heater is come online now. Amp's now got full power and currently is nice and stable at 76 watts out the wall. So mains voltage today 242 volts. So it's pulling 338 milliamps or 0.338 amps. So the 1 amp mains fuse is correct. Just monitor that for a minute. Now we know in these circuits rectifier valves can be quite stressed. So it'll be interesting to find out what downstream of this rectifier valve is causing these to fail, because as the customer said to me, he's replaced these a couple of times now. So do we have an issue in the high voltage rail? We need to get a schematic really to see how Vox have done these, work it out. There is no standby switch, which should be a good thing. Less stress on the rectifier, but we'll see. I'm going to leave the amp now just running as it is. I'm going to keep monitoring it while I do some research and come back. The one thing about the CompuBias is that it's maybe quite lazy in measuring biasing because it's so easy to plug this thing and read. And I actually don't like that. I don't like that I haven't been doing my manual bias calculations. So it's interesting to get back into it. Anyway, so I've taken some bias readings in the amplifier. And immediately we see a problem in that our anode to cathode voltage, 343 volts each side. Our screen voltage is 5 volts higher. That's no good. No wonder it's cooking output valves, right? So we have to get that lower. Easiest way to do that will be to increase the screen stoppers from 100 ohms. We'll calculate the screen current and then we can work out an appropriate value to get that number below. We need to drop it by 6 volts really as a minimum, right? Our cathode resistor, it's 130 ohms, but it measures 127.5, and we've got a 12.05 volt drop across it. Ohm's law, volts is current times resistance, and Joule's law, watts is voltage times current. So that's what we need to do. That's what we need to do our sums today. So first thing we need to know is the amount of current flowing through the cathode resistor, and it's a shared cathode resistor for both output valves. So for current we need voltage divided by resistance, so 12.05 divided by 127.5 ohms means we've got 0.0945 amps or 94.5 milliamps flowing through that cathode resistor. All right, we've got 2 valves, so we divide that by 2, assuming it's an equal split, puts us at 47.25, so 0.0047, no, not 0.0, added an extra one there. There you go, 5 amps per valve. We then times that by our anode to cathode voltage, 343, means these are running at, so our power anode plus screen dissipation is 16.2 watts. Now these are EL84s are 12 watts, so we divide that by 12, means we are running at 135%. Wow, screaming hot. Right, so we know why we've got a discoloration of the output valves, the EL84s. They're running far too hot. We've also got screens that are running far too hot relative to the anodes. They need to, again, that figure must be at least 1 volt lower than the anode to cathode voltage. That answers a lot of questions, doesn't it? That really does. So if we look at the correct schematic for the amplifier, it says it's a very interesting configuration, this. So here's our rectifier valve here. We've got a high voltage coming off here. It's filtered by C1, which is a 22 microfarad capacitor there. Then the entire B plus rail is filtered by this choke, this 8 Henry choke here. Now it says HT, this point here. This point, if we follow it down, goes to the center tap of our output transformer, which has a secondary filter there, its own dedicated filter cap at C21. The anodes obviously fed up to here, but our screens, look, are also fed from the same point. So our HT node here is feeding both the anodes and the screens. The only difference, of course, is the screens themselves have got R21 and R22, these 100 ohm screen droppers there, and you can see they're just using these switches here to feed the anodes either from that point or directly from the center tap. You see how they've done that? So yeah, we've got our 130 ohm resistor there. So it's a 3 watt bypassed by a 47 microfarad cap there. These EL84s were bound to be stressed, absolutely bound to be stressed. So now that 12 watt figure I gave you, so the maximum for an EL84 is 12 watts, but you've actually got a little bit extra because the screens are not included in that number, so you can probably go to 13. But when you've got a triode mode and the screens are running from the same supply, that number drops down. So yeah, no good. We need to fix this. So no wonder our rectifier valve is being stressed. Got a lot of current being drawn through the output valves, plus the rest of the amp is drawing current as well. So my suggestion here to fix this amp, I don't think there's an underlying fault that's developed. I think it was built in from the beginning. I think we've got a poorly designed output stage that's just running far too hot. Far too hot, too much going on, too much stress being put on this poor little EZ81 rectifier valve, right? We've then got aging filter caps and other components as well, which are starting to wear out, starting to get tired. So this amp needs a jolly good goddamn service, excuse the language. So I think that's what we're going to do. We're going to recommend to this customer a new set of EL84s, a new rectifier valve. We're going to, about time this thing gets an electrolytic recap, and then we're going to calm everything down, just cool it off, stop stressing it so much. There's no need to try and squeeze so much out of it. These amps sound really good when they're running well within their limits. So that's what we're going to do. So I'm going to go back to customer now, make my suggestion, and I think on top of the impedance mismatch that we discovered, we had a 16 ohm speaker plugged into the 8 ohm tap of the output transformer. So we've got even more stress put on this circuit. I think that's where we are. I think that's the issue. So good news and bad news. Good news is that we haven't got anything major to do. It's all basic service work. The bad news is it's going to cost the customer probably a little bit more money than he wanted to spend, but I suspect he was expecting that anyway. So thank you very much for watching. I hope you enjoyed this. I will put the resolution to this repair in a future video. But I need to get this all filmed and edited and whatnot uploaded, ready to come out on Good Friday. Thanks for watching. Right, I just thought we'd try upping the cathode resistor. So I've gone from 130 ohms. The next E12 value up was 150. I've gone up to 180, so 2 steps higher. It's in there. Anyway, I have done the sums. I've done the numbers. Obviously, when current decreases, voltage increases. We know that. So our anode to cathode voltage has risen by about 9 volts. The screen voltage is still higher than that, again by 5 volts, so that's tracking. Our voltage drop across the resistor, 13.32, is actually measures 181 ohms, means we've dropped the total current down from 94.5 milliamps to 73.6. So we're now running at 36.8 milliamps per valve, which puts us at 12.95 watts. So we've cooled that down from 135% to 108. So I will try the next value up, which is 220 ohms, to see where we end up with that, see if that puts us in a nicer place. But already, I think if we can drop our screen voltage down, that number is going to drop slightly anyway, and we're going to just be stressing this thing far less than it ever was. So yeah, just wanted to show you that before we signed off, but there you go. Already making improvements.